everyone, my name is Shatabdi. I'm a second year medical student. So today we're going to be discussing about the topic magnetism. So the first thing that comes to our mind when we talk about magnetism is how we have measured it. Like till now, we knew that the compass that we have consists of a north pole and a south pole, and accordingly, it shows us the direction by the arrow that is deflected accordingly, right? So when we talk about compasses, we like talk about a faint idea that we have about magnetism. Then when we were younger, we used to play with certain magnets, and we used to be really like intrigued by the fact that how they used to like attract each other through a certain amount of distance and then get attached to each other when slowly the distance was decreased. So all these gave us a faint idea of what magnetism is. Today we're going to know that in terms of physics what it means. So this North Pole and South Pole, like the whole concept of compass, it came because the Earth actually in itself is a huge magnet. And when I say it's a huge magnet, it means that it has a North Pole and a South Pole. Okay. So now later on, I think you've studied in geography also and physics also. You will study that apart from the actual north or south that is there, there's also a magnetic south and a magnetic north. So those are in the opposite direction. So what I'm trying to tell you is that if this is the north pole of the earth and this is the south pole, then the magnetic north and the magnetic south are opposite. Like this is the MS and this is the MN. And these particular poles, since they are near to the actual north and south pole, so they only help us by deflecting the compass, and accordingly we get the directions of places. So the whole concept of compass is because the earth in itself is a huge magnet. Okay. So compass needle gets deflected when brought near a bar magnet. Yes, we have seen it. It is in fact a small bar magnet. Like the compass needle in itself is a small bar magnet. So as a result of which, the ends of the compass point approximately towards the north and the south directions. The end pointing towards the north is called the north seeking or north pole, and that of the south is called the south seeking or the south pole. Obviously, for deflection to happen, the substance also needs to have some magnetic properties, right? So if say this is a bar magnet and this is a compass, so the fact that it is deflecting, like the arrow is deflecting accordingly when you are keeping it near to the south pole or keeping it near to the north pole, is because this in itself has some magnetic properties, and that is the reason why it is said that it also is a small bar magnet. Okay. So magnetic field is a quantity that has both direction and magnitude. The direction of the magnetic field is taken to be the direction in which the north pole of the compass moves inside it. Okay. So therefore it is taken by convention that the field lines emerge from the north pole and merge at the south pole. So if you look at this picture, you'll understand that all the field lines are drawn coming out of the north pole, right? If you can understand here, see here it's going out, here it's also going out, but since it has to reach the south pole, it is in the form of curved lines. Basically these curves you cannot see because they are huge, but it will also be something like this. So inside the magnet, the direction of the field lines from south pole to north pole, thus they are closed curves. So the only reason as to how it will become a closed curve is if the circle is completed, right? So you can very well understand that inside the bar magnet the lines will go like this, and thus it will form a series of closed curves. So this gives us an idea of the magnetic field. So now wherever you keep the compass will accordingly direct itself north and south. So accordingly it will deflect, right? When you bring it very, very close to the magnet, it will deflect in a very higher speed. That is because as in when you bring it closer to the magnetic field intensity increases. As you can see here, how these lines here and here, the intensity is so huge, and as you move away, the field line distances get decreased. So the magnetic field intensity also decreases. The relative strength of the magnetic field is shown by the degree of closeness of the field lines. The field is stronger, that is, the force acting on the pole of another magnet placed is greater where the field lines are crowded. So this is what I was talking to you about, that if this is a magnet, north and south, so all the lines are coming like this. So here you can see how it is so much crowded, but as and when you move away from the magnet, the field lines, the distance between the field lines increases, and if distance between field lines increase, it means that magnetic intensity or magnetic field intensity decreases. So if you put a compass here, the deflection that it will cause will be far lesser than what it will cause if you place a compass here. Okay, so this is the whole concept. So in the same way, as and when if you go towards the North Pole or towards the South Pole, you'll understand that the magnetic field is increasing a lot. It's deflecting a lot. But if you stay near the core of the earth, it will not deflect that much. Okay. Also, an important point to note here is that no two field lines are found to cross each other. If they did, it would mean that at the point of intersection, the compass needle would point towards two directions, which is not possible. So what they're saying is that, see, so this drawing is obviously not accurate because the magnetic field lines can never cross each other. So what they're trying to say is that if there was a field line coming like this and another field line coming like this, so if you put a compass here, then in which direction will the compass deflect? Because it has at this point two field lines, right? So it cannot deflect like this, right? So it cannot point towards two direction because every unique field line will have a unique path, a unique deflection point, and a unique direction towards which the compass will point, right? So obviously it cannot point at two directions at the same time, as a result of which the field lines will never cross each other. They are always parallel to each other or in the form of closed curves. Magnetic field due to a current carrying conductor. So now this topic is very, very important. So what is seen here is that in the later on we'll understand how current produces magnetism, and at the same time a magnetic field can also produce current if you move something at a very, very high speed. So for now we are saying that a current carrying conductor produces a magnetic field. Now how was this discovered? This was basically discovered by again placing a compass near a current carrying conductor. It showed that as and when you were in decreasing the distance between the current carrying conductor and the compass was deflecting at a very high rate. Okay, and then when you were taking it away, it was deflecting, like the needle was deflecting at a slow rate. Again, when the direction of the current was changed, like here you can see that the direction is from x to y. When the direction was changed from y to x, it was seen that the compass's needle had gone to the opposite direction was deflecting in the opposite direction but in speed. And then when you have again taken away the compass slowly, it was seen that it was still deflecting in the opposite direction but in a slower magnitude. So this is how it was discovered that a current carrying conductor also has a magnetic field. Now what is the direction of the magnetic field? So before that, we find that the deflection in the needle also changes. In fact, if current is increased, the deflection also increases. Yes, it indicates that the magnitude of the magnetic field produced at a given point increases as the current through the wire increases. So what it is saying is that if, say, 1 ampere is given, so the needle will deflect, say if this was the original position, the needle will deflect this much. If the current is increased, then they are saying that the deflection is more, right? So more the current, more the deflection. Also, greater the distance, lesser the deflection, because you are taking it away and you're also decreasing the magnetic field intensity as in when you move the compass away. Okay, so now we come to the direction, like how the direction of the magnetic field is calculated. So if you can see this diagram, you'll understand that what they are doing is that if they, for example, wrap the fingers around the magnetic around the straight current carrying conductor such that the thumb is pointing towards the direction of the current, then the magnetic field lines correspond to the curling of the thumbs. So if you look at the camera here, so in this picture they are showing that the current is going from X to Y, which is in this direction, the direction of my thumb, and the curl of the fingers of my right hand are in this way, right? So they are moving clockwise here. So in the same way, if you look at this picture, you'll understand that they are moving like this. Again, if the direction was like this, you can very well understand if it was from Y to X, then the curl would have been anti-clockwise, right? The curl would have been anti-clockwise. So you can try it at home. It's known as the right hand thumb rule. This is how we find the magnetic field due to current carrying conductor. Straight. You have to remember this. So here also you can see that the magnetic field is produced and these are the magnetic field lines. What happens to the deflection of the needle if the compass is moved away from the copper wire but the current through the wire remains the same? This also we have discussed that as and when you are taking, so suppose these are the magnetic field lines. It will be something like this. So here the field lines are very concentrated, right? So as and when you are moving away from the current carrying conductor, so if you place here, the deflection will be, say, like this. If you place it here, it will be like this. If you place it here, it will be like this. So as and when you are moving the compass away, the magnetic field intensity, when you're moving it away, the magnetic field intensity is decreasing, right? As distance is increasing. So we can say that it's inversely proportional, or distance is inversely proportional to the magnetic field intensity. So to answer this question will be that the deflection of the needle decreases as the compass is moved away from the copper wire, but the current through the wire remains the same. Now we talk about the right hand thumb rule, which we discussed a while back. that imagine that you're holding a current carrying straight conductor in your right hand such that the thumb points towards the direction of the current as I showed you. Then your fingers will wrap around the conductor in the direction of the magnetic field lines of the magnetic field. This is known as the right hand thumb rule. So by this you can understand the direction. See, this is anti-clockwise, thumb pointing upwards, and this is clockwise, thumb pointing downwards. Okay. So again, if this is given in the xy plane, but if we draw it in the y, we cannot draw it in the yz plane, but I'll just show you that if the current is going through the paper, so later on in the higher classes you'll see that if a current carrying straight conductor is for example said to pass through the paper, then it will look something like this. Like we denote it like this, as if an arrow is going inside the paper. So if an arrow goes inside the paper, then we just see the back of the arrow, right, which is the cross point. And if a conductor is coming out of the paper, it's coming towards you, so in that case we see this part. So this is the point direction. This is how you can remember it. So in this case, what is happening is that you again place your thumb like this if the current is going inside the paper, and you curl your fingers, right? You curl your fingers like this, so it is again coming towards your clockwise direction. Current is flowing clockwise. Sorry, the magnetic fields are clockwise. And again, if it is coming towards you, like the coming out of the paper, the current carrying conductor is coming out of the paper, then it will be clockwise. You can just try it at home, it's very simple. So yeah. Sorry, this will be anti-clockwise. No, if it is going inside, then it is anti-clockwise. Actually, if you see it like this, so in the paper, what's happening is that if you put your thumb like this, then it will be in the clockwise direction towards you. Like when you see it, it is in the clockwise direction, right? And if it is coming out, then towards you, it will be in the anti-clockwise direction. So this arrow will just change. Yeah. So that is it about the right hand thumb rule. Now is the magnetic field due to a current carrying circular loop. So we studied about the straight current carrying conductor. Now we'll study about the circular loop. So every point on the wire carrying the current would give rise to the magnetic field. We know that. And they will appear as straight lines at the center of the loop. So at the center of the loop, if you see, it is absolutely a straight line. By applying the right hand rule, it is easy to check that every section of the wire contributes to the magnetic field lines in the same direction within the loop. So if you touch, so first we have to see in which direction the current is flowing. The current is coming from here, so it is like this, flowing like this, right? So if you take, suppose I've named this point as point A. So if you take the point A, then what is happening is that if you look at the camera, it is moving like this, right? This is the direction of the current, and your fingers are curling like this. So they are moving like this. And at the same time, if you touch any of the current carrying conductors, you can understand, like you try it with every section and it will give you the according field line directions. Okay. So another thing to remember here is that here we are just we just saw one loop. So sometimes they are going to give you something like this. So there are a lot of turns. Okay, so this is not a very accurate diagram. If I try to draw it like this, basically. So if there is a circular coil having n turns, then the field produces n times as large as that produced by a single turn. This is because the current in each circular turn has the same direction and the field due to each turn then just adds up. So if I tell you that this same circular loop is given three turns, then the magnetic field, if in the first case I told you is 5 Tesla, then now it becomes 5 into 3 equals to 15 Tesla. So Tesla, you'll later on understand that it is the unit of magnetic field. Okay. So we talked about straight current carrying conductor. We talked about circular loop. Now we will see magnetic field due to a current in a solenoid. So solenoid, if you see, it is a coil of many circular turns of insulated copper wire wrapped closely in the shape of a cylinder. This is called a solenoid. So you can see so many turns. Since they are so closely packed, it almost seems as if it is a cylinder. Okay. So it has found some similarity between a bar magnet as well. So since its conformation is like this, that it acts like a bar magnet, and what all do we know about the bar magnet is that it has a north pole and a south pole, and that field lines emerge from the north pole and go towards the south pole, and the same thing. So the thing is that how do we understand which is the north pole and which is the south pole? Okay, so what we do is, again we apply the thumb rule here, and since the current is moving, so if I draw it like this here at this point, I'm just drawing a magnified version. Sorry, this is the positive one. Yeah. So negative and positive. So basically the current is coming out of here. You know that the current always comes out of the positive terminal, and the direction of the current you have to very specifically understand, because that is the main thing. That is how you will understand the direction of the magnetic field. So it is going like this, right? So you again apply the thumb rule at this point. What will you see? That if it is going like this, then the curling is like this, and this is the direction, right? So at every point you see that the field lines are like this. So it appears as if the field lines are all getting inserted or converging at this end. Say this is end A, this is end B. So it seems as if they are all inserting or converging at point A, and they are all emerging out of point B. Like if you apply the thumb rule at each and every point, you'll understand this. So inserting or converging at A and emerging at B will give us only one outcome, and that is that A is the south pole and B is the north pole. Okay. So now if you see the picture, you can understand that here they have given that this is the south pole and this is the north pole. This is the corresponding bar magnet comparison, where this is the south pole, this is the north pole, where the lines are all inserted into the south pole and emerging out of the north pole. So this understanding is very important, because we get a lot of questions saying that this is a solenoid, so tell me the direction of the magnetic field. So always apply the right hand thumb rule and try to understand where all the arrows are, or where all the curling of your fingers are happening. So that will give you the direction of the magnetic field. Okay. So A strong magnetic field produced inside a solenoid can be used to magnetize a piece of magnetic material like soft iron when placed inside the coil. So, solenoid, we saw it is like this, right? So, I am just drawing very less number of turns. In general, solenoid has a lot of turns. So what they are saying here is that since we have already understood how current produces a magnetic field, so if we place a block of iron like this, okay, if you are placing it inside the solenoid, and suppose like there are n number of turns here, okay. So the strong magnetic field produced inside the solenoid is used to magnetize a piece of magnetic material. So you know the soft iron already has some magnetic properties, right? A magnet can attract it, which in the higher classes you'll understand that they have some magnetic particles inside them. So they are basically magnetized in a very concentrated magnetic field. Like we know here so many magnetic field, like the intensity, right? The intensity of the magnetic field is huge. So what happens is that a soft iron block or anything that any magnetic material that you keep inside the solenoid, it will develop magnetic, like strong magnetic properties. It will magnetize, okay. It can be acted as a magnet in itself. The magnet so formed is called an electromagnet. So we formed it by converting electrical energy to magnetic energy, right? So since we have converted the electrical energy to magnetic energy, now it will also act as a magnet, but it has a condition. The condition is that as soon as you switch off the key, as soon as there is no current flowing through the conductor, it will almost be like a few seconds later, the iron will stop acting as a magnet altogether. So the condition of producing an electromagnet is that as so long as the current is flowing through the conductor, the iron will be magnetized. As soon as you switch off the current, immediately or a few seconds later, it will again get demagnetized. So this is a shortcoming of an electromagnet. But so long as the current is flowing, it produces very strong magnetic properties inside the soft iron. So we come to the end of the discussion for today. In our next class, we're going to be continuing with the magnetic field only. We'll learn more about the strength and how to calculate the magnetic field. So thank you for watching.